My name is Phil Burk, and I've been programming music and audio software for a long time, both in game industry, academia, working on experimental music systems, and also working at Google Android on Android Audio. And so I want to talk to you a bit today about using Kotlin Compose Multiplatform to sort of restore an old online drum machine. So let me there we go. Okay, so I'm going to cover what is this app. It was called the Web Drum, and it uses. I'm going to talk about Kotlin Compose as a multi-platform tool. I'm going to move my web camera over, so I'm not looking to the side. I'm also going to talk about a multi-platform audio solution called KC Audio Bridge, and some networking issues, talk about other problems and the solutions I found. And then if there's time, we'll do a little online drum jam at transjam.com. So the web drum is a multiplayer system that allows each green box is a person, and multiple people can be in a room jamming together and sharing a drum pattern. And all of this communication is managed using something called the transjam server. So there is a central server for brokering all of this communication between the users. This is what the UI looked like in year 2000. Year 2000. So there's sort of multiple tracks. Some are mono tracks for most of the drums, and there's a couple multi-pitch tracks for supporting melody. And you can do things like polyrhythms by having 7 notes in 11 beats or things like that. The timeline for this, the WebDrum first release was in 1997. So this was actually one of the first interactive sort of multiplayer audio programs on the web. The first version was pretty complex with envelope editors. It was a little simplified, easier version was released in the year 2000, presented at ICMC and various conferences. It required a native plugin, and in order to do the audio and the synthesis, and this native plugin required releasing 11 versions of this plugin for different browsers, different platforms. So it was a bit of a barrier for people to use it. So we converted to pure Java in 2010, but in 2015, Java applets were removed from the browser. So suddenly the WebDrum did not work, and for the past 10 years, it's been unavailable. But just recently, I converted it to Kotlin and Compose, and so now it runs again on the web, and it also runs on Android and on the desktop. So Kotlin Compose really came to the rescue here. It's a great program by JetBrains. This work in cooperation with Google. The work is done in Android Studio, but it's not specific to Android. You can also just develop for the desktop or for the web. So it allows you to write a program that will run on all of these various systems. The UI part of it is provided by Compose, and it's a kind of functional language that came out of Jetpack Compose that was written for Android, but it works now on all these different platforms. It works really great, but the big problem is there was no cross-platform support for audio, which for most of the people here, that's a bit of a showstopper. So created something called KC Kotlin Compose Audio Bridge, and it's available on GitHub, and I'm sharing that. So the way it's implemented, Kotlin has these expect and actual classes. So it's kind of like a Java interface. So the expect class defines the UI for the class or a function, and then the actual class is the implementation for specific platforms, like on desktop or for WebAssembly. The code is available on GitHub, and you can try it out. There's some demos and some documentation on how to get it to work. The API is very simple, and it's really the lowest common denominator sort of API here. You create an audio bridge, you open it, you get a stereo floating point stream. You can query the sample rate, which is usually 44,100, but might be different for some platforms. And then you launch a job. In this case, it's kind of a coroutine, and you start the audio, and then you render your data into a float array, and you write it and do blocking writes to the audio bridge. If all the data is not written, you can do a little sleep and then try again to write. So that's it. That's basically the API. So it's very simple to use, and and in some cases the implementation was simple, but others not. So this is the implementation for desktop. It uses the JVM, Java Virtual Machine, and we make use of the Java Sound API. So this was pretty simple. We just convert the float array to a short array and then to a byte array and then output it through Java Sound. On Android, it was also pretty straightforward. The Android audio track has a method that you can write, which is a floating point array. And it takes sample offsets instead of frames. So you just have to convert from frames to samples. Actually, you don't. The audio bridge takes care of this. So that's the implementation, most of the implementation for the Android part. The web part was a lot trickier. I wanted to use WebAudio for its good low latency and performance, but the realm and the thread in which the audio worklet node is working is very restricted, and you can't just communicate with it directly like you can, with the Java Sound implementation. And so the way to get around this was by communicating to this restricted domain through a FIFO. So the audio data is written through a FIFO. The FIFO is an atomic FIFO, which for audio developers, if you don't know, it is a very, very helpful design pattern. Basically, each thread can control one cursor into the data. So the application is writing data, and it is the only thread that updates this frames written. And the audio worklet node is reading the data, and it updates the cursor for the frames read. And they can both read both cursors, so they know when and where to read and write. So WebAssembly has a mechanism for sharing data between threads, and it's called a shared array buffer. And it's a critical data structure for doing this. So we use a float, and you can wrap it in like a float array or an int array. So we use a float array for the audio PCM data, and then an int array to contain the read and write cursors, the buffer capacity, underflow count, things like that. Now, in order to access these, you need to use the Java Sound atomic functions so that you get the proper flushing from the cache and the memory barriers and so on, so that these different processes can see each other. So we're doing an atomics load to get basically the frames read, so we know this is the callback, so it knows where it read the last time, and it converts that to an index into the float array, reads the data, and then it updates the data in the for the frames read. In order to do this, there's so much security in the browser, which is an unfortunate necessity. But one of the things you'll have to do to enable this is to provide a .htaccess file in the folder that contains your applet. I include one in the KC audio bridge. It's an invisible file, so it's easy to miss if you just drag the files over from the Finder. But this enables this cross-origin capability, and it magically enables the shared array buffer. Future for KC Audio Bridge, this is an experimental API, and It may change. There is we may also look at adding native desktop support using port audio, that which would give it a little better performance and make it not require a Java virtual machine for desktop applications. The iOS support will be nice. I'm not very familiar with iOS coming from Android, but maybe someone could look at the GitHub repository and volunteer to help support that. Audio input, it'd be nice to have, but there's so many security issues around audio input that would have just complicated things. So it does not currently support that, but maybe in the future. So other changes were also needed to get to convert this old Java applet to a Kotlin Compose multi-platform applet. And one of the things that's very different in this new environment is that you can't just use regular threads. You have to use coroutines, which is kind of a cooperative multitasking system, and you have to be a little bit more deliberate about creating these threads. And so you're constantly going in and out of these functions, and you can't just go into a thread and sit there because it might block the UI or it might block some other coroutine. So because you're going in and out of these functions, it's much easier to implement them as a state machine. This is also another design pattern that can be very helpful for real-time audio or interactive audio, where you may have a lot of information that you're keeping track of, but you can encode that as a single state variable, and then you just transition around these states by updating the state variable, and then maybe using a switch statement to process differently based on the state variable. And then there's communication between these state machines. So data may come in from the network client using the Kotlin Compose state flow, which is a kind of way for data to flow from other coroutines up to the UI, or in this case to the state machine, and then there are callbacks from the network state machine up to the UI state machine. So the UI may be switching screens from a login screen to the drum screen, and the network state machine is busy trying to set up various rooms or broker communication between the applets. So these separate state machines can communicate. And then there's another coroutine that's actually doing the sequencing and the drum audio synthesis. So another difference is that the original WebDrum used JSyn for instruments, which is a Java synthesizer that was written also back in the 90s. And it's because it's Java, it won't get converted to to the WebAssembly. The Kotlin can target all these various WebAssembly or native code or Java bytecode, but it has to be Kotlin. And so what I did is I took the JSyn Java code, generated the sounds, generated samples of those sounds, and then the Kotlin code is just playing back those original JSyn samples. So the sounds are the same, they're just not being generated on the fly. I'm actually thinking about converting JSyn to KSyn, and since most of it is math and DSP, it should convert pretty simply, and then I would be able to use the synthesis code in a variety of multi-platform applications. The network connection is obviously required for this multiplayer code, and I used ktor to implement a TCP/IP connection to the Transgem server. That worked great on Android and on desktop, but on the web, again, things were different. So I had to use a WebSocket. So ktor supports a WebSocket implementation both as a client and a server. So I wrote a very simple relay that runs on the same server as the Transgem TCP/IP server, and it just relays messages coming in from the WebSocket, and it sends them at the TCP or TCP/IP to the server, and vice versa. So it's just a classic relay doesn't really do any processing. It's just sitting in the middle and passing messages back and forth. And that works, that seemed to work pretty well. Regular Java exceptions don't work, so you just have to sort of rewrite your own class of exceptions for your own custom IO exceptions and so on. I was able to come up with something that looks a lot like the original WebDrum. So this is version 3, and my goal was to recreate the original WebDrum. I did make a few small changes. I moved the sort of global controls like the tempo control and the loudness controls, things like that, up to the top. And that allowed me to have the bottom part be scrollable and to integrate it with a chat message. In version 4 of the WebDrum, I'll probably rethink the UI and maybe use a more modern approach for the UI. But my goal in this case was actually to kind of recreate the original, the original WebDrum, but in this using modern technology so that it could run on multiple platforms. The line count, the Kotlin code is a bit smaller than the Java code, but that may be because I converted the Java instruments to just playing samples. So there was a lot of Java instruments that were not in the Kotlin code. So to conclude, what are we doing on time? I think I'm pretty good on time. So to conclude, I find that using Kotlin Compose is great for generating, portable audio and music apps that run on Android. It supposedly can target iOS, desktop applications. There was really very little that had to change. Just this backend audio connection, and the KC Audio Bridge handles that for most applications if they just have to output audio. So please contribute if you can, not money, just expertise. Take a look at the KC Audio Bridge, try it out. Maybe we can make improvements there. And if there's time, I would like to invite people to join a small jam at this link. So it's at transjam.com. And I'll go there. I think I'm still, this is still being broadcast. So if you go to transjam.com, you'll see this link. There's links to the slides, GitHub. I'm going to run the WebDrum app. I'll run this one. I'll put in my name, Phil. Okay, there's no existing room, so I'm going to create a room. And this can, I can, it's a typical drum pattern, but if you, oh, okay, another user has arrived, great. So I can actually chat and send messages to people, see Javier has joined. There may be multiple rooms if more than, I think there's a maximum of maybe 6 or 8 people in a room. So if one room's full, just create a new room. And so if you may need to click this little own button here. That allows you to control that drum. Once you click it, then you can go in and start, filling in some of these different sounds. So I may change my timbale here to a zoop sound. And it can also convert this to a Chebyshev polynomial sound. So you can type, device to others to control a track, or you can map out a strategy like, oh, let's speed up, let's slow down. Why don't you, try this, or let's try polyrhythms, things like that, and turn this down just a little bit. So I found that the chat part of it was, I think, a really important part of the WebDrum because it really helps people realize that they're not just interacting with a bot, that they're actually jamming with other people. Just I'll point out some things about the interface here. So you can do things like have 16 notes in say 8 beats, and you'll notice that this now is a shorter row. So then that lets you do faster faster beats, or I could maybe do like 12 notes in 8 beats, and then I can kind of do various polyrhythms. There's left-right panning and stuff you can do, obviously. These will let you select various instruments. Ring mod bell is so there's FM bells, ring mod bells, a plucked gong, claps, which is a stochastically generated clap sound. So lots of different options there. This fader here is a yes/no fader, and I'll let you can experiment with that and kind of find what that does. You might be able to imagine what it does, and you may be right. Also, there's a solo button, so if you want to just listen to what you're generating, you can solo that. That will not affect what other people hear. It just allows you to, do a sanity check on like what your tracks are doing, or you can also solo other people's tracks. So that's the basic UI. When you can hide the chat or not. And this looks very similar on Android, except that the chat covers a bigger area of the screen and it's scrollable. So that's one of the major differences. Oh, also you can change the tempo. I can slow it down, and I can change, to a 5-tone just intonation tuning system, if that's your thing. You can change the bass, the fundamental for that. Oh, these over here are loudness controls, so you can make very loud or very soft sounds. I'm going to depart this room. Thank you, Rocco. And I can see that they're okay. Yeah. So at the moment, the people are in the bonkers room. So but you can come in and move between rooms. So I think maybe we can move to Q&A, Jim, I think.